Welcome to the first video of the next unit. We are going to be talking in this unit about functions and transformations in a general sense, so establishing what a function is and looking at different transformations that can be applied to them regardless of what the original function happens to be. So to start things off, we're going to have to actually distinguish between a mathematical relation and a function. And we've kind of used the terminology interchangeably up until this point because understanding and appreciating the distinction wasn't necessarily a primary focus for you in earlier years. But a relation, mathematically, is any relationship between sets of values. So typically when we will be looking at it, it's going to be an expressed connection between some x values and y values. Now that can show up in a few different ways. So on this slide, I've included some examples of relations, and I've actually tried to include a diverse selection of different ways a relation could be evident. So we established it's a link between x and y values. So a table of values, as you see in the top left, is probably one of the more direct connections to that definition. We can very clearly see which x's go with which y's. It's very intuitive, and we've been using those for quite a long time. To the right of that, you'll notice I've drawn a scatter plot. So scatter plot is actually the graphical equivalent of a table of values. It's still showing a connection between x's and y's, but it's doing it in a graphical form. Moving sort of down and to the right of that, you'll see that I have this group of points, a set of points in the curly brackets or braces, as they're appropriately called. That's another way of presenting a set of points. So it's like a table of values, but it has each ordered pair listed separately in a set, in a mathematical set. And so that's another way of showing a relation. It's still establishing a connection between x's and y's. Now those three examples I just gave are only connecting very specific x's with very specific y's. There's no equation or pattern that corresponds to those. In fact, I actually just generated all those numbers randomly, so there's no rhyme or reason to the numbers that I picked. The three things along the bottom, though, you'll notice there's two graphs and then an equation just by itself. All three of those are relations as well, because they're all based on an equation that directly links x's and y's. And here there is a foundational pattern. I could substitute a value for x into one of those equations and solve for the corresponding value of y. Now, any smooth curve is an example of a relation. So you'll notice that there's one that's completely closed off. It's kind of like an oval or a racetrack. So that's an example of a relation as well. So is the item to the right, which kind of looks like a quadratic that got dented inward on both sides. Any smooth curve is a connection of infinitely many points. And so to that end, it is still a relationship between x and y. Now the two on the right that are shaded in blue are perhaps the most abstract of the bunch. Those are actually graphs of inequalities. So the one that looks like a square is the graph of when x is greater than 0 and y is greater than 0. So essentially the first quadrant on my Cartesian plane. Now, anything that is a shaded region is a grouping of infinitely many points in that space. This inequality graph is actually saying it includes all the points from the origin down both axes infinitely and everything in between. And so that is also a relationship between x and y values. It's a fairly broad relationship, but it is still a relationship between x's and y's. The very rightmost one is an interesting inequality. I actually graphed that because it's all the x values greater than -3, but then all the points that are contained between those two lines. So it makes that triangular region. But any shaded region like that, based on inequalities, is still a relationship between x's and y's. So relations can show up in many different forms. So a function is a little bit different by definition. A function is considered a subtype of a relation, or you could say all functions are relations, but not all relations are functions. So functions fit under the umbrella of what a relation is. So you've got all those different things I showed you on the last slide. Functions fit within those. Not all of those things I showed you were functions, but all of them were relations. By definition, a function is a one-to-one mapping of x values to y values. So what that means, there's a few different words there that you probably haven't heard before, a few different phrases. A mapping is basically implying that each x value is connected through some sort of operations to a y value. The fact that it's one-to-one means that each x value is only ever going to connect to a single y value. And so what I've drawn here is actually the beginnings of a mapping diagram. And so here you can see that I've connected all the x values to a y value. So the x value of 1 maps to a y value of 4. The x value of 2 maps to a y value of -2. 3 maps to 4, and 4 maps to 5. And so that's just showing that those numbers are connected somehow through some property, through some operation. An x value of 1 turns into a y value of 4, and so on. And so this mapping diagram is actually how we would show some details of a function and how the x values connect to those y values. So this is actually something you'll see fairly common as you learn more and more about functions. Now, when we talk about the x values of a function, that whole set of all the x values, we refer to it as the domain. And the y values we refer to as the range, or sometimes you'll see it referred to as the codomain. But for the majority of textbooks that you'll come across, I suspect it will be referred to as the range. So your domain are all the x values that work for a function. The range are all the y values you'll get as outputs of a function. So here's an example of a function just drawn in a mapping. So each x value is mapping over to one y value. The x values are not connecting towards more than one y value. So 1 as an x value only goes over to a single y value. Same for 2, same for 3, same for 4. You can tell that pretty easily because there's only one arrow leaving each x value. And so there, that tells us that we are not actually having any more than that one-to-one relationship. Each x value is going over to a single y value. And so that tells me that this would be an example of a function. This next one, though, you can see the mapping diagram's a little bit more cluttered because there are a lot more arrows coming off of my x values to y values. And so the huge red flags here as to this not being a function would be the x values of 2 and 4. I can see there are multiple arrows leaving those x values, which means the x value is mapping over to multiple y values. And by definition, that's no longer a one-to-one connection. And so at that point, we know that it is actually not a function. If that x value could change into multiple y values, it's not a function anymore, it's just a relation. Now, it's all well and good to look at a mapping diagram and be able to trace arrows, but the fact of the matter is, you'll be working far more often with algebraic equations or with graphical representations for functions and relations. And if you want to be able to tell the difference, you have to know what you're looking for in an equation and what you're looking for in a graph. So in general, what you're going to be looking for in an equation is actually fairly easy to spot. I've listed a whole bunch of relations here. Some of the types that are here you've seen, some of them you haven't. So for example, the first one is a circle. The next one after that, y equals 3x minus 5, that would be a line. There's another line in there on the right and a quadratic, but then there's a few other ones you likely haven't seen. The 3 at the bottom, I think, should be largely unfamiliar. And so looking at them all, you might be very puzzled as to what constitutes a function in this case. And the way you can tell actually is based on whether there's an exponent on the y. Typically, if there's an even exponent on the y in an equation, it means that if you were to substitute an x value into that equation, you would end up solving for multiple y values at the end. The easiest spot to see that is in this one here at the bottom. If I was to substitute in an x value of 4, and solve for the corresponding y values, what I would actually discover is I have plus or minus 2 that work. And that's showing me that a single x value connects to more than one y value. So I know that this one, by having an exponent of 2 on the y, that one's not a function. And so is this one up here. The circle is not a function. All of the other ones that are listed there are functions. So that's what you look for if you're trying to determine algebraically if something is a function. But what if you have a graph and you want to figure it out? Well, then what you should be doing is using what's called the vertical line test, which is actually a very simple graphical way to determine if a relation is a function. So here are the graphs of two relations here. I've got a quadratic on the left and what appears to be a rotated quadratic on the right. So it almost looks like it's been rotated 90 degrees, and that's why it's going out sideways instead. Now the key here is that each x value should only ever correspond to one y value, which means if I put a vertical line through this relation, if that vertical line can hit more than 1 point on the relation, it means it's not a function. So here I have vertical lines drawn in. You can see there's no spot on the quadratic on the left where I could put a vertical line and it hits the curve twice. It's only ever going to hit it once. However, the relation on the right, you can see that vertical line hits twice. It hits once in the upper part, once in the lower part. And so by making contact twice, it's showing that for that one x value, there are two possible y values, which again means that it cannot be a function. So the one on the left is a function, the one on the right is not a function, it is just a relation. So now you have an algebraic way of testing if something is a function. You also have a graphical way of testing if something is a function. And so you should be able to use both of those methods to move forward and analyze functions fully.